Good afternoon. I'm Andrew Head, a first-year PhD student with the Berkeley Institute of Design. And today I'm going to present research that I've done with my collaborators at Berkeley and Adobe in 3D printing interactive devices. So we use interactive devices throughout our days, from mice and game controllers to laser pointers and MIDI keyboards. And each of these have a novel form that's specifically tailored to the digital task that you want to perform. And today, in some prototyping processes, you might start out making your next great interactive device by making a 3D model of it in a CAD program like SolidWorks, declaring the design as well as the dimensions. And then once you've done that, modern-day 3D printing techniques allow you to quickly iterate through multiple forms of the skeleton. However, there's still something standing in the way of rapid prototyping. To have an interactive device that's truly interactive, you have to instrument it with microcontrollers, hookups, a hookup wire, and sensors. And this is unfortunately not something that a machine can do these days. So at BID, we ask, what are ways that we can 3D print interactive devices without wires? Berkeley's well equipped to ask this question. Up here, I'm showing the Invention Lab, which is actually going to be open later today. The Invention Lab is a hacker and maker space for students to work on hardware. And among other things, we have half a dozen gorgeous 3D printers, including these two professional level ones that we use to support our current research. But back to the 3D printed devices. Because we can't 3D print electronics, but we can 3D print mechanisms, we ask, how can we sense mechanisms? We come up with two ideas: vision and sound. This is Sauron, a tool that we developed to help designers design and optimize the layout of joysticks, buttons, and direction pads on custom 3D printed controllers. This is a game controller that was designed with Sauron. With a plugin, you add this virtual camera to the back of the device. And then once you've done that, you can see the different controls that are visible from that camera and the places that you should instrument it with additional mirrors in order to see the other controls within the device. And with this, we've been able to build things like 3D printed game controllers and DJ mixing boards that communicate with the computer through OSC events. But beyond vision, what are our other options? Well, if you ever use a device like a game controller, you'll note that the different components like joysticks and buttons will make different sounds. How can we actually quantify these and convert them into events, interaction events? We respond to this with the Lamello framework for input components and acoustic sensing. Lamello components are named after lamellophonic instruments, which are things like thumb pianos, which have varying sized tongues that generate different frequencies. So we use these tines of different sizes to give control events. Here's an example of a button printed with the Lamello technique. You can see as you press down on the button, it vibrates this cantilever, vibrating the full control. We can make more complex controls like this dial here by taking different sized tines, arranging them radially around the center, and then having this striker that goes around and strikes each of these. How do we end up distinguishing between each of these different tines? Well, as it turns out, you can predict the frequency of a tine from its geometry. Once you know a couple of the material properties, like the Young's modulus, you can just vary the length in order to get a different frequency for that tine. So on the computation side of things, we collect a sound after a strike from a contact microphone. We convert this into the frequency domain. Here you can see along the x-axis there's time, on the y-axis there's frequency, and then the intensity of the color is the energy of that frequency. And so by just comparing the frequency spectrums of these different strikes, you can find out what interaction event has just occurred by the tine that has just been struck. Each of these events is preceded with this wideband transient, followed by this long period of resonance where we wait until that resonance in order to perform that classification. Here's an example of one of the Lamello sliders in action, and with audio from the contact mic. How well does this work in practice? Here you can see the accuracy for two different controls, one in blue and one in orange. We get mixed results in the upper frequencies, which are on the right side of each of the devices. But we actually get pretty good results for a subset of the tines. This is something that we want to extend across the entire control. In the future, we hope to incorporate Lamello inputs into the tangible inputs that we deal with in our everyday life, like light switches and volume controls, and to continue to ask the question about how we can sense 3D printed interaction without needing wires. Thank you.